Hello everyone, myself Vishal Khare from SSR College of Arts, Commerce Science Silvassa. Welcome to tutorial on numerical methods and its application. Topic 1.2 Bisection Method. Introduction. In scientific and engineering studies, a frequently occurring problem is to find the roots of equation of the form fx is equal to 0. If fx is quadratic, cubic or a biquadratic expression, then algebraic formulae are available for expressing the roots in terms of the coefficients. On the other hand, when fx is a polynomial of higher degree or an expression involving transcendental functions, algebraic methods are not available, and recourse must be taken to find the roots by approximate methods. This chapter is concerned with the description of several numerical methods for the solution of equation of the form given in the equation 1, where fx is algebraic or transcendental or a combination of both. Now, algebraic function of the form fnx is equal to a0 x to the power n plus a1 x to the power n minus 1 plus a2 x to the power n minus 2 plus and so on plus an minus 1 x plus an are called polynomials, and we discuss some special methods for determining their roots. A non-algebraic function is called a transcendental function, e.g. fx is equal to ln x cube minus 0.7, phi x is equal to e to the power minus 0.5x minus 5x, psi x is equal to sin square x minus x square minus 2, etc. This function involves logarithmic function, this function involves exponential function, and this function involves trigonometrical function, etc. The roots of equation 2 may be either real or complex. We discuss method of finding a real roots of algebraic or transcendental equation, and also methods of determining all real and complex root of polynomials. Solution of system of nonlinear equations will be considered at the end of the chapter. If fx is a polynomial of the form equation 2, the following results from the theory of equation would be useful in locating its roots. Number 1. Every polynomial equation of the nth degree has n and only n roots. Number 2. If n is odd, the polynomial equation has at least one real root whose sign is opposite to that of the last term. Number 3. If n is even and constant term is negative, then the equation has at least one positive root and at least one negative root. Number 4. If the polynomial equation has a real coefficient, then imaginary roots occurs in pairs, and b rational coefficients, then irrational roots occurs in pairs. Descartes' rule of sign. A polynomial equation fx equal to 0 cannot have more number of positive real roots than the number of changes of sign in the coefficient of fx. B. In A above, fx equal to 0 cannot have more number of negative real roots than the number of changes of signs in the coefficient of f of x minus x. We will see the example of Descartes' rule in the next lectures. Bisection method. This method is based on theorem which states that if a function fx is continuous between a and b, and fa and fb are of opposite signs, then there exists at least one root between a and b. For definiteness, let fb be negative, let fa be negative and fb be positive, then the root lies between a and b, and let its approximate value be given by x0 is equal to a plus b by 2. If f of x0 is equal to 0, we conclude that x0 is a root of the equation fx equal to 0. Otherwise, the root lies between x0 and b, or between x0 and a, depending on whether f of x0 is negative or positive. We designate this new interval as a1 b1, whose length is mod b minus a by 2. As before, this is bisected at x1, and the new interval, which will be exactly half the length of the previous one. We repeat this process until the latest interval, which contains the root, is as small as desired, say epsilon. It is clear that the interval width is reduced by a factor of 1/2 at each step, and at the end of the nth step, the new interval will be an bn of length mod b minus a by 2 raised to the power n. We then have mod b minus a upon 2 raised to the power n less than or equal to epsilon, which gives on simplification n is greater than or equal to log base e mod b minus a upon epsilon upon log base e 2, means natural log. Equation 3 gives the number of iteration required to achieve an accuracy. For example, if mod b minus a is equal to 1 and epsilon is equal to 0.001, then it can be seen that n is greater than or equal to 10. The method is shown graphically here. Here the interval is a and b, and you can see fa is negative and fb is positive. So roots lies between a and b. Now x0 can be found by adding a plus b and dividing it by 2, means the value of x0 is equal to a plus b by 2. So on this x0 the value of fx is negative. So now root lies between f of x0 and b, because they are of opposite sign. The value of function on these points are of opposite sign. Now we have to again add x0 and b and divide it by 2. So we will get here x1. Now at x1 you can see the value of the function is positive. So the value of function, value of f of x1 is positive and value of f of x0 is negative. Therefore roots lies between x0 and x1. Again we have to add these two x0 and x1 and divide it by 2. So we will get new point x2. So on x2 the value of function is negative. Therefore roots lies between x0 and x1 and x2. So same way we have to proceed. So we will get a desired root. It should be noted that this method always succeeds. If there are more roots than one in the interval, bisection method finds one of the roots. It can be easily programmed using the following computational steps. Number 1, choose two real number a and b such that fa into fb less than 0, means these fa and fb are of opposite sign. Number 2, set xr is equal to a plus b by 2. Number 3, point a, if fa into fxr is less than 0, means of opposite sign, the roots lies between a and xr. Then set b is equal to xr and go to step number 2 above. Point b, if fa into fxr greater than 0, the root lies in the interval xr and b. Then set a is equal to xr and go to step number 2. Point number c, if fa into f of xr is equal to 0, it means that xr is the root of the equation, fx equal to 0, and the computation may be terminated. In practical problems, the roots may not be exact, so that condition c above is never satisfied. In such a case, we need to adopt a criterion for deciding when to terminate the computation. A convenient criterion is to compute the percentage error EP defined by EP is equal to XR dash minus XR upon XR dash cross 100%, where XR dash is the new value of XR. The computations can be terminated when R become less than a prescribed tolerance, say EP. In addition, the maximum number of iteration may also be specified in advance. So in the next lectures we will see some examples. Thank you.